Hello and welcome to today's tutorial. So today I will going to talk on the expectation of random process. So before going to the expectation of random process, let us see what is the independence of the random process. If the random process is an independent, statistically independent, then from the definition of random variable, so what we can apply for the random process. So let us switch back to our screen here. So independence of random process. Now for example, let us say if two events, that is A and B, are statistically independent or statistically independent, then if it is statistically independent, then we know that from the probability of the random variables or the outcomes. Just a minute, let me select the right one. So if A and B are the two events, and if it is independent, means it doesn't depend on the occurrence of any other event. So such kind of events we call it as independent events. So then its probability of A intersection with B is given as the probability of A into probability of B. It means it is now the product of probability of individual events. The intersection of the two event probabilities should also equal to the product of the probability of individual events. So now if you apply the same thing to a very general rule, then the probability of say AI intersection with AJ, then this is equal to the probability of AI into the probability of AJ, where I and J are not the same terms, where I and J are not equals. So these are the different events. So now if we apply this to our random process, to a multivariate random process, then its density function can be written as fx of t1. We know this is a multivariate density function for two time instants. So that is x of t1 with x of one more time instant, that is t2 of x1, and x2 is equal to, so it is for a two random, it is for a bivariate case. So then this will result in, that is x of t1 of x1 into the product of fx of t2 of x2. So if you continue this for n events, then for n events it will be, let me move this down. So if it is for n events, then it will be fx of, then it is fx of t1, then x of t2, x dash 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 up to x of tn of say x1, x2 dash dash up to xn, which is equal to the product of these individual density function, that is fx of t1 of x1 into fx of t2 fx of t2 of x2, then dash 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 into fx of tn into xn. So now you can see the density function is a product of individual density function. Now same thing if you apply for a two different random process, then with the different time instance, then what we get, this independence equation will be, it is same as this. So let me write here, let me move this section down, then I'll get here as fx x of t1, then dash 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 up to x of tn, then into y, the another random process, that is y of t1 dash 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 y of tn dash of say x1 dash xn of y1 dash up to yn is now equal to, now it is the product of the two different random variables of different time sets. So now that is defined as, that is fx of t1, x of t2, so on, it continues dash dash up to x of tn of x1, x2 dash dash xn into, then we will get, that is fi of t1 dash y of t2 dash dash up to say y of tn dash of y1 y2 dash dash yn. So now you can see it is the product of two different density functions of random process. All these each of these random process is now a different instant of time. So this is about the random process if they are independent. Now let us see the expectation. So let me clear this board. Now let's see the expectation of random process. Expectation of random process. So here the expectation of random process for a multivariate random variable, it is with respect to time t. So let us see that before going to this, let us revise the random process for the expectation of the random variables. So we know that for a random variable we used to write this, x bar represents the expectation of x bar represents the expectation of x. So this is nothing but mu x. So this is an integral of say minus infinity to plus infinity x with multiplied with the density function, that is fx of x with dx. Okay, so this is the expectation of a random variable x. Now if it is same thing, if we were finding an expectation of difference of say random variable x minus with its mean mx whole square, then its expectation value will result in integration of minus infinity plus infinity, and same thing is multiplied, that is x minus mu x whole square into fx of x into dx. Now remember here, this capital X represents the random variable and this small x represents the observation of that random variable. Now if we write the variance of this, then variance of x is defined as, that is sigma x square is equal to, that is an expectation of, that is x minus mu x whole square. So now it means that the expectation of this is nothing but it is the variance. Now if the same thing if we apply for the random process, then what do we get? Let me save this page here so that we can use it later. So then the mean of a random process, it is represented as mu x of t, because here the random process depends on time t, then it is an expectation of then it is an expectation of x of t is equal to integral of minus infinity to plus infinity, that is x with fx of t, its density function. Now it is density function, it is not just x, it is x of t of x into dx. And if you look at the variance of this random process, that is x squared, then it is nothing but the variance of the x of t is equal to its integral of minus infinity to plus infinity of x minus mu x of t whole square into fx of t of x into dx. So here the mean and the random variable of the random process depends on parameter of time t. So we can note that here it depends on time t. Now the same thing if you apply for a bivariate case, that is if I apply for a bivariated random, different random uh, uh, process, or it might be the same random variable with different time instance. Then in for such cases, if you apply, so then expectation of x of t1 and x of t2, then what is its mean or expectation? So if we see, so now it is a same random variable, that is x, but at different time instance that we have taken the two different n symbol points, we have taken two n symbol sets we have taken. So then it will become a double integral. It is not single integral, it is double integral. So this definition holds good with the bivariate random variables. So from that we can extract this um equation. So it's a double integral minus infinity to plus infinity. Now it is the two observations, that is x1 and x2, that is multiplied with the density function, that is fx of t1 with x of t2 of x1 x2 into dx1 into dx1 into dx2. So now you can see that here when we compare this with a single random process with a bivariate or multivariate random process, what is the difference is that in the single random process it is the single integral, and here in a bivariate case it is a double integral with x1 x2. Now if it is same thing, if we represent this in terms of two different random variables, then it is an expectation of then x of say t1 and then y of t2, it is equal to integral again minus infinity, this is minus infinity to plus infinity, then this is x1 y2 into f x of t1 y of t2, that is of x1 y2 into dx1 with dy2. So this is a expectation for two random processes at different time instance. So now let us look into the stationary process. What is the meaning of stationary process? So let me save this page here. I'll call this as page 5. So let me take the new page here. So we'll talk about the stationarity. Stationarity. So what is the definition of stationarity? It means if the expectation if the expectation of random process is independent of say time or independent of change of time, so such a process we call it as a stationary process. So the definition is when the statistical properties, or the other definition is that the statistical properties of the process do not change with time is called stationary process. So let me write here the definition. I'll write both the definitions here. So stationarity as it is used here, or carries the sense that expectations are invariant with changes in time. So this can adopt the PDF and calculate the expectation change of time. So let me write the second definition also here. So second definition also makes sense here. Now when the statistical properties of a process do not change with time, it is called stationary process. So if the statistical properties remains to be same, if it does not change with respect to time, then it is called the stationary process. For example, we have taken in the previous tutorial, we have taken an example of, say, the variation of the temperature over the day. So if we record this temperature over multiple days, then we get something like this. So we have three different observations over the time. So now if I take at one time instance, say t1, then if the statistical properties at this point, and the statistical, if I take another point, let me call this as t2, if the statistical properties here, if it remains to be same, then we call it as a stationary process. Now let us see that in terms of the definition. So first let us see the stationary of order n. So we will see the stationary of order n. So it means that the bivariate PDF of order n is invariant with respect to arbitrary time shift ts. Now for example, if this time t is shifted by some time, if it is shifted by some time, say ts, then it is invariant. So that is what it means. So let me write the definition here. So it means that a multivariate, let me expand this. If the multivariate PDF of order n is invariant with an arbitrary shift in time of ts, so then we call it as a stationary process. So now let us take a random process x of t is observed at different time instance. So now for example, we have taken the two time instance only. Now if it is observed at the different time instance, so t1, t2, t3, and likewise if we take this up to tn, if it is observed at the different time instance, then its density function is defined as, how do we define this density function? Then density function, it is defined as, that is fx of t1, then x of t2 up to, say, dash dash. This we already defined. Now x of tn of x1, x2, x3 dash dash xn. So remember, this is also called as x of t1 or x1, this is x2, this is x3, and this is xn. Okay, so these instance or the observation points, we call it as we have given this name. Now if you suppose if this is shifted by each one of these time instants, say t1, t2, t3 and tn are shifted by some time, say plus ts, so plus ts is the interval. If it is shifted, then how does it define? Then it is fx of t1 plus ts, then x of t2 plus ts. Likewise, if the nth time instant, that is tn plus ts, then that is x1 x2 dash dash xn, if this is equal to, if whatever the statistical properties that is having at these points, and after the shift of that ts, if we get a new ts point somewhere here, then if that is equal to this, then we say that it is a stationary process or a stationary random process. So this we have defined for a multivariate case because there are multiple time instants. So uh, n symbol is nothing but like this. We have taken the three observations. If we take infinite observations, and for those infinite observations, if we take some time instance, say t1, of all these points will form the n symbol data set. And likewise, if we take like this n sample points, so these are nothing but the sample points here. So if we take these n sample points, and for these sample points, if we apply a shift of this density function, and that density function is same as the density function at that time instant, so then we say it's a stationary process. Now let us look into the stationary of order 1. So let me save this page here. So it is page 6. So let me go to the new page here. So let us talk about the stationary of order 1. Stationary of order 1. So stationary of order 1 implies that we have taken now from the previous what we had written um, the observations here like this. So you have one observation, two observation, like this you have n number of infinite number of observations. So for this infinite number of observations, so we have taken only one sample point. So we have taken a one sample point here. So at all these, so that represents a first order stationary. So this we have taken this as only at one time instant, so this defines a first order stationary. So its density function is defined as fx of t plus ts. So if I call this t1 itself, because since it is only the one time instant, I can also call this as t. So if this t is shifted by some time instant, say ts, then at that ts point, so that is a t plus ts point, sample point, if um, then its statistical properties, if it is similar to x of t of x, so then it is also equal to a random variable. Now it has become independent of time. It means there is no effect of time. If there is no change, then it means there is no effect of time. So then we can define this, the density function, in terms of a random variable, that is just fx of x. If you see that the arbitrary term, that is the time t, is absent in this case. So now if the first order case, if it is a stationary, then we can write it is independent of time t or independent of time shift. So then its mean function, we know that the mean of x of t is equal to, it is integral of say minus infinity to plus infinity, then it is x into fx of x into dx. This we already written previously. So now we know that this is an expectation of a random process. So now the expectation of a random process, that is nothing but mean. If it is free of time or if it is independent of time, then mu x of t will become a constant. So then now it will become mu of x. It is similar to the mean of a random variable. So likewise, the variance also becomes independent of time, then it is the sigma x of t square will become the sigma x square. So these are the important points. So if it is a stationary, if a random process is a stationary, then its mean and the variance will become constant. So that is what we have to remember here. So let us look into the stationary of order 2. Let me save this page here. So this is page 7. So let me go to new page here. So let's see the stationary of order 2. Stationary of order 2, it means we are considering a bivariate case. So now in this case, what we are doing is we have taken the n observations. So we have taken the n observations here. So some observations, and we have taken a time instant, say t1, and we have taken one more time instant t2. So that results in a bivariate case for a single random variable. So that is defined as, its density function is defined as fx. Now if each of these time instants are shifted by time ts, now this is also shifted by time ts, this is also shifted by time ts, then if at both these points, the new points, if the statistical properties remains to be constant or unchanged, then it is a stationary process. So then it is fx of t1 plus ts, then x of t2 plus ts of x1 x2 is equal to, this is equal to, now it is fx of t1 x of t2 of x1 x2. Then now if it is invariance of time shift, so let us do little analysis here and let us relate this to a correlation term. So now let us consider that t1 plus ts as a time instant, say this is equal to, say, time t. Now what we have done is that this t1 plus ts, I'll call it as time t. It means now the first time instant or the first sample time, I call this as just t, and this is the second time instant, I'll call this as t plus tau, the new term. I'll call this as t plus tau. So then this t2 plus ts, so this can be written as say t1 is equal to sorry, not t1, so ts is equal to, it is t minus t1. So then t2 plus ts, so t2 plus ts, sorry, so t2 plus ts can be written as, now I'm going to substitute for ts, so it is t2 plus ts is nothing but t minus t1. So now I can write this as t minus, t plus, I'll take this t2 minus t1. Now the difference in this time, that is t1 and t2, I call this as the difference of time as tau. So now this, I can write this as t plus tau. So now if you substitute this t plus tau in our previous equation, in this first equation, then what happens to our first equation, that is, so now it is fx of t1 with x of t2 of, say, x1 x2 is equal to, now it is, so the right hand side and left hand side are interchanged, so don't worry, so it's all same. Then in this case it is t1 plus s can be written as fx of t, and t2 plus ts can be written as x of, it is written as x of t plus, it is written as x of t plus tau of x1 and x2. Okay, so now you can say this. Now let us talk about White's and stationary random process. So let me save this page here. So let me call this as page 8. So let me get the new page. So let us talk about White's and stationary random process. White's and stationary random process. So White's and stationary random process. So it is defined as like most of the time the autocorrelation function and the mean of the random process is considered. So the process may not be stationary in strict sense. Still, the mean and autocorrelation functions are independent of the shift of time. It means the autocorrelation process and the mean are independent of shift of time, though it is not exactly the stationary process. So for example, it might be a fast moving or fast variation signal, and one might be a slow varying signal. Now if we look into this case here, so now if this is a slow moving signal and this is a fast moving signal. So if we see here, if we take the statistical properties here, it may not be constant at all the times, but if I take a statistical point at these 2 points here at 2 time instance, say this is t1 and the second one I call this as t2. If I see the statistical process, then I call this as a strict stationary process, or a stationary process of order 2 or order 1. But in the second waveform it may not be same, so the statistical properties may not be same. In such case, we will going to use the mean and the random. We will use the mean in autocorrelation. So now let me write the definition here for White's and stationary. So the process may not be stationary in strict sense. Still, the mean and autocorrelation functions are independent of shift of time origin. So such process is called wide sense stationary process. So wide sense stationary process. So for wide sense stationary process, the expectation of say a random process that is x of t is nothing but, from the previous definition, it's a constant that is mu of x, or expectation of say a bivariate case, that is expectation of x of t with x of t plus tau. X of t plus tau will result in, sorry for handwriting, I am using the mouse, so then expectation, this is similar to an expectation of x of t1 with x of t2. Okay, now in this case, if the tau becomes equal to 0, then if the difference becomes 0, basically if the tau becomes 0, if the difference becomes 0, then it will become an expectation of the same random variable, that is x of t with x of t. Then this will become an expectation of x squared. So from the variance definition, we know that the definition of variance, that is of a random variable, variance of random variable, that is sigma x square, is given as an expectation of x squared minus mu x square. So now if you apply that equation here in this case, so we will get, this is nothing but the variance plus mean of a random variable. So this is what we say. So here the first order, second order stationary can be also a random process of first order and second order stationary can be a wide sense stationary process, but reverse is not true. It means a wide sense stationary process cannot be a strict sense stationary, or it cannot be a stationary process. So this we have to understand. Okay, so thank you for watching this tutorial. So in the next tutorial we're going to talk about the autocorrelation function of a random process. Thank you so much for watching this tutorial.